Hello, everybody, and welcome to the user dissemination workshop of the FFG ASAP Space4Wind research project. Today we are going to talk about the cooperative research project between Rheologic and Uranium Research about predicting the best spots and optimal positioning for wind power plants. Who are we in the research project? We are actually two companies, Rheologic and Uranium Research. My name is Andras Schwabert. I'm the CEO of Rheologic GmbH, and my co-workers are Christian, Markus, and Sahir. We've been working on this project for 1.5 years now and are reaching the final stages and have interesting results to present today. From Uranium Research, from the Institute of Digital Technologies, Remote Sensing and Geoinformation, we have Heinz and Katharina with us today, and a representative from Green Energy Lab. Let me introduce our company first. What is Rheologic good at? What is Uranium Research good at? Meaning, what are our core competencies? In Rheologic, we deal a lot with wind power, wind comfort, and wind danger, especially in the built environment where tall-rise buildings can pose a threat to wind conditions on pedestrian level. We simulate urban microclimate, meaning nighttime cooling or daytime urban heat island effects. We simulate process intensification in the pharmaceutical industry, especially intensification of mixing and homogenization processes and clean room design for pharmaceutical applications. Uranium Research core technologies or core knowledge lies in the processing of remote sensing data, validation of remote sensing services, different Copernicus services, and generally environmental monitoring. Interestingly, some of our projects already showed some overlap because we simulated recently part of urban microclimate in a part of Vienna, the so-called Donaufeld. And if you look at the graphic below, the big graphic is an infrared image of Vienna. And we simulated a small part of Vienna, Donaufeld, and pretty well predicted the nighttime cooling there. As you can see, the part of Donaufeld that is dark blue is around 3.5 degrees cooler than its surroundings, and also new built and planned buildings will actually receive some of that cool air during the nighttime. So this is just a short overview of what we actually do with our models and our simulation expertise. The Space4Wind project started from an idea that was born in the ESA Big Hackathon in 2022 for space applications. This is probably not a typical space application, because we want to simulate wind over complex landscape using satellite data and globally available weather models. Some of you already know that services like these are already available worldwide. Some of those are available only in Europe. The worldwide available service is, for example, the Global Wind Atlas, which gives you wind potential around the globe with a relatively high resolution. And the new European Wind Atlas does the same for Europe with an even higher resolution. So one of the questions that arises, why do something new or do something different? The thing we want to actually plug in our new models into is in the data pipeline of creating a bankable wind resource assessment. So presenting to an investor why it's worth the investment in a wind power plant on a special site. And why is that so hard? If you look at the graphics below, this is a standard from 2010 that deals around predicting the annual energy production. And the CFD is just one part of those process steps. So the simulation alone is just a part of the planning phase of a complete wind power plant. But it's a very important step because the amortization rate really depends on how much wind you can harvest and what the uncertainty of this harvest will be. It's a small step in the planning, or just a puzzle in the planning of a wind power plant, but one that has huge influence on the amortization rate and the break-even point of this wind power plant. Why is that so complex, and why is it in so many stages and so much science about? The thing is actually in the complexity of the terrain, because the surface features influence the local wind speed to a high degree. The closer you go to the surface, the more influence you have on those power plants. The higher up you go, the less the influence of surface features gets. Our idea was to get from different satellite data a very detailed map of the surface features and use that as a boundary condition in our simulations. We wanted to recode the standard wind modeling roughness classes to something that can be used in a simulation in the meter scale resolution. If you look at the Global Wind Atlas, you see a pixel size which is in the hundreds of meters. But we know from experience from other projects that within those pixels, the wind power can drastically change. So we need higher resolution derived from Earth observation and satellite data. The actual problem description. What do we have as problem? We have a complex problem at hand. Why is this problem complex? And why are there seemingly easy solutions already available, like the Global Wind Atlas? Let's look at the different puzzles that make up a good wind simulation. This is a collage here. From different things, an engineer that wants to simulate local wind power with a high precision needs to know and consider in advance. So you have a certain kind of landscape. On top, you see the Wind Research Park Lichteneck in Lower Austria, which is often regarded as a very complex site for wind power. Why is the site very complex? Because if you look at the ground features, a lot is going on. You have forests, you have fields, you have very curved surfaces and a floating terrain, if you like, yeah, floating hills. The distribution of the vegetation is completely inhomogeneous. So you have fields, clear cuts, dense forests, and all overlaid with a very complex terrain structure, very wrinkled structure. What does a wind engineer need to consider? First, the data acquisition. How do I get the surface data? Which quality does the surface data need? Is the surface data freely available? Is the surface data available globally? What about the vegetation? How can I derive the vegetation zones from satellite data? Is it sufficiently resolved? Is it up to date? Are the heights of the trees correct and usable in a wide range? What about the wind data? How do I really get the wind as input data? Because for my CFD simulation, which stands for computational fluid dynamics, I need some boundary conditions. I need to know roughly how the wind goes there. The better I know the wind, the better I know the vegetation, the better I know the surface structure, the more correct my simulation will be. What about CFD models? Are the models suitable for the terrain, for the problem at hand? Which parameters do I need to consider in the model? Do I need to consider heat fluxes? Do I need to consider changing forest density? What about the directional resolution? How many directions do I need to look at? What is the wind distribution like? And I'm not even talking about the software here. How do I automate this? Because our approach was running very complex simulations in an automated way to reach results better than the state of the art. How reliable is that? Will it run every time for every place? What hardware do I need to run this? Can I run it on my computer under the desk? Do I need a cluster? Do I need to build a cluster? What about the software? What about the dependencies? So as you can see, I'm not even going into the bloody details of the simulation here, but we have a complex intertwined problem here we need to solve. And this is the engineering point of view. But what does the customer want? Customer actually doesn't really care about all those complexity. The customer wants simplicity. What is the customer interested in? The customer is interested in the annual energy production there. I have a wind energy converter. The zoning tells me wind park is suitable here. The distances to residential area is high. It's not a protected zone. Promising wind, if I look at the wind atlas there, what if I put my plant there? What is the annualized energy production? Which energy converter is optimal for that site? What's the height where I can harvest most of the wind energy? And then the most important questions for the bankable wind energy report. What is the uncertainty of the yield? Meaning, if I predict the annual energy production, what is the uncertainty? What's the plus minus every year? What is the expected error rate I have? And then, of course, where are the best spots to place the energy converters in a complex landscape? On the right, you can see an image that is colored by average wind speed from one sector. And you can see by changing just the position by just a few hundred meters, you reach places where it's absolutely unfeasible to put any wind energy converter there. Moving again a few hundred meters away, perfect spots for wind energy converters. And it changes so quickly over the landscape that models with the resolution of the Global Wind Atlas completely fail to even resolve those changes. At this point, I'd like to hand over to Heinz, and he will tell you a little bit about the core knowledge of Ioneo and how that fits into our simulation and ideation of the data flow.
Okay, thanks, Anders. So I share my screen. Yes, so I will now talk a little bit about Earth observation methods suitable for this wind prediction. Of course, I'm only talking about, as you will see in a second, about the surface representation and not on all the Earth observation which is put in the wind prediction per se. So from modeling wind speeds and things like that. So we are I'm concentrating on surface, and there the key term, of course, is surface roughness, or more precisely surface roughness length, which can be derived from, for instance, 3D information. And 3D information can come, if we think of Earth observation, from LiDAR data, which is mainly airborne LiDAR data. Of course, this is more or less the optimum we can reach with respect to accuracy and resolution. 3D information can also be derived from stereometric images, be it airborne or satellite-based. Interferometry, so meaning using satellite SAR data is also an option to get 3D information, or a lot of other methods which are maybe not so common, but especially these DeepL or machine learning approaches come quite popular in the last few years. So this is one option to get the surface length, but surface roughness length, but of course also the surface itself. Another option would be that we derive this surface roughness length from simply recoding land cover classifications. And as input for our land cover classification, we again can use airborne imagery or satellite-based imagery. And the third option would be that we go away from optical images to again SAR images and try to get to retrieve surface roughness from SAR backscatter. And of course, you have the ability to combine all these methods to get out the best of it. Yeah, so one basic term is, of course, this normalized digital surface model, or NDSM, as it's usually called. So this is more or less everything above the ground, and the ground is, in technical terms, called digital terrain model. And we assume that the digital terrain model is more a static model of the Earth, so it changes not that often. And it can be extracted from a DSM, and the DSM is the digital surface model. So this is really including all the trees, buildings, and everything else. So, and the DSM, in contrary to the DTM, is a more dynamic model because, of course, new buildings, clear cuts, and so on immediately change the DSM. To give you some examples now from what we derived during this project for one test site. So this is test site Handarm. I just start with an overview of the auto image from the Austrian surveying bureau. So the energy converter is more or less in the center of this 10 by 10 square kilometer image. And on the right-hand side, you already see an NDSM. So this would be one perfect input for this roughness length estimation. This is derived from airborne LiDAR data and scaled from 0 to 40 meters above ground. So, and in comparison, if we now think about other areas, so not only maybe Europe, but outside Europe, we have to think of other sources to get an NDSM. And one option could be that we use the global available COPDEM as a surface representation and the so-called FABDEM as the DTM representation. And if we make the difference of that, we again end up with NDSM. And maybe if I switch a little bit between these two sources, you immediately see the differences. And I also calculated the differences itself. And you see, okay, this is roughly, so the global available COPDEM, FABDEM roughly approximate the NDSM. But if we go really into detail, and this is requested for the anticipated application, this NDSM from these sources have problems. So not to say that they will fail in certain complex terrains. So the other method is that we try to recode land cover classifications global available land cover classifications could be this ESA world cover, for instance, but there are of course many others. But the idea is that each land cover class is then assigned to a roughness class, and therefore we get quite high resolution, I would say, especially high resolution. Unfortunately, if the classes are mixed up, of course, our surface roughness lengths will also have problems in these areas. Again, an example for Handarm, and I also highlighted here then the inner area of our simulation, or the simulation of rheologic. So this would be our land cover classification from using the auto images, so high resolution optical images. And this would be the classification from ESA world cover. It looks similar, of course. If we zoom in our inner part, then you immediately see the differences. So, of course, if you have higher resolution input, you get out more details about buildings and the shape of the forests and clear cuts and roads in the forest and things like that. And this, of course, is very important for the following simulation. Yeah, and with that, last slide here, I just did the comparison between the different methods and or say the data sources we have and the methods applied to them and the coverage. And of course, this has also an impact on the costs. And one point I did not mention yet is, of course, the topicality of the data. So we saw in at least one test site that the forest cover changes over these 10 years of simulations. And here, of course, remote sensing has quite important rules, especially this Space4Wind remote sensing, because you get a frequent update of your land cover classification and can also then detect the changes in this classification over time. And this is maybe more important than really have the boundaries of the forest for one instance in time very accurate. So, and with that, I give back to Andras.
Thank you, Hans. And back to our data flow. This is the state of research and automation we have reached in the project so far. So we combine Earth observation data and CFD models in an automated way to get out the annual energy production at any point on the globe. We are using data that is available with global coverage, and this is how it roughly works. So for the Earth data and geometry, we use surface roughness classes. Those are derived by machine learning models. We use surface description that is available globally, which is based on Copernicus DEM with 30-meter resolution. We use Joanneum Research's RSG software to generate geotiffs as input for our 3D models. And in those steps, reprojection happens, rescaling, cutting, and void filling, meaning preparing the surface data in a format that can be used for us to generate something that is shown on the right, a 3D geometry. On this 3D geometry, we put a forest canopy, and we automatically create a turntable style input with 10 kilometers diameter. This is shown above. What you see there has a diameter of 10 kilometers with a core zone of 2 kilometers, and in the center is the actual wind power plant. And this is all done in an automated way. What happens after that is we get wind data from global circulation models. In this case, we use ERA5 on an hourly basis over the last 10 years. Average those, dissect them into 16 different sectors, and use those as input for 16 different simulations, which we map on each other based on the frequency of their occurrence. And this all happens automatically in a large eddy simulation and yields something that can be seen on the right, which is the wind speed distribution at the site of the wind energy converter. And from that, you can calculate the annualized energy output. The interesting thing now is how accurate are our results. We wanted to have a model that is, first of all, applicable worldwide, and second of all, have an accuracy that is needed by bankable wind energy reports. So we're looking specifically at complex terrain in our simulations. Why do we do that? Because the problem for simple terrain is already solved by other solutions. In simple terrain, many models give very accurate predictions, the global wind atlas included. A simple terrain is something that is rather flat, with very small hills, with very low steepness, low changes in land use, something that is mostly flat. If you look at Austria, most of the energy production happens in Niederösterreich, Burgenland. Those areas give probably 85% of Austrian energy production, but most of the sites are in simple terrain. So the eastern part of Austria is rather flat. The terrain doesn't change really quickly. This can be predicted easily, and the repowering and the prediction of wind speed at higher heights is a solved problem. Our solution is applicable there, but it's actually not needed there. We wanted to go in an area where there are high wind speeds and complex terrain, which are hard to predict by standard solutions. And for that, we were looking at two classical validation benchmarks for complex terrain. In the upper right, you can see the Bolund Hill in Denmark, and below the Askerwein Hill in Scotland. Those are really classics known in the wind industry for some time. The Askerwein Hill in Scotland was covered by a very extensive measurement campaign from 1982 to 1983. And the Bolund Hill in Denmark is a rather new measurement campaign around 2010. This hill in Denmark is a model hill. If you look at the real size of this hill, this is only 12 meters. But most of the time, the flow comes from the western side. And on the western side, you have something that is actually a cliff. So you have an extreme change in steepness. You have something locally that is highly rugged. And this ruggedness index will follow us through the next slides. The ruggedness index gives you a number of how complex the terrain is. If you have gently flowing hills, like the Askerwein Hill in Scotland, you will get a rather low ruggedness index. This is 3.3 over a 2-kilometer radius, 2-kilometer diameter. If you look at the Bolund Hill in Denmark, on the circle that covers the hill, the roughness index is at 13.9. This is the classical example of very complex terrain. And many CFD models fail in this terrain. So we are using specialized CFD models that can deal with this high complexity terrain. And what we do is we validate our simulation approach, meaning we compare the results our simulation yields. The result is the average wind speed from a certain sector. Compare this with measurements. You see two plots here, one for the Poland Hill and the bottom plot is for the Askewine Hill, where the wind speed, the simulated wind speeds, are those with the solid lines, are compared to measured values. Values are obtained from wind mast measurements. And as you can see, the models can quite well predict the wind speed. Meaning, if I only know the landscape, the land use classes, the vegetation, and this can be based from Earth observational data, and given certain wind velocity as input speeds, I can predict the average wind speed there. And with that, I can predict the annual energy production of a wind energy converter there. And to gain confidence in our model, we did that for several validation sites around the globe, especially focusing on complex terrain, meaning terrain that is wrinkled, that is not really nice to standard models which are used in wind power. And I'd like to present the validation sites now. The first validation site lies in the western parts of the United States, almost on the west coast. You can see, I think, the ocean in the background. This is Nacelle Ridge. And we were looking at specifically the Tall Tower dataset, TTD, which covers many tall wind mast measurements around the globe. And we're comparing our simulation, the green line, against the measurement, purple line at Nacelle Ridge. We almost hit the measurement result there. On the right, you can see the ruggedness spectrum of Nacelle Ridge Hill. You can see that there is a very steep change in terrain on the western end. You can also see that there is vegetation change, so this is typical complex terrain. Even more complex and very close to the Nacelle Ridge site is Megla, also in the western part of the US, close to the sea, strong changes in forest density, very high terrain ruggedness index. And as you can see, our simulation result, the green line, overpredicts the wind velocity there. And this is natural and goes all into a statistic we will show you later. Another forest site. This is Mountain Lake Biological Station in Virginia, covered by the NEON network. This is the National Earth Observation Network in US, where data from wind masts is provided over a longer period to compare to the simulation results. This met mast is actually located in the forest, directly in the forest from 0.3 meters to treetop level. And as you can see, the simulation hits the measurement data pretty well for the NEON site MLBS. SOAP is very special because this is a site that showed after simulation it's not really usable for wind power, but we wanted a method that can also distinguish places which are not usable for wind power and those which are perfectly usable for wind power. As you can see, the accuracy varies, but the variation is not very large on an absolute scale. We are talking about 1 meter per second wind velocity here. This is absolutely too low for wind power, but we are still in a range that covers the statistical deviation here. And we have two outtrain sites. Energie Steiermark provided us with direct measurement of a wind power plant, of a wind energy converter at 70 meters height above ground at the Handarm. You can see a drone photo of Handarm here. This is definitely complex terrain. You can see part of the wind park Handarm there. You can see how the tree cover changes, and you can see the measurement and our simulation results with pretty good coincidence. Lichteneck, this data was provided by FH Technikum Wien. This is one of the most complex sites, not looking at the terrain ruggedness index, but at the vegetation and at the way the vegetation changes with the landscape there. This is really hard to predict, also because the wind measurement there was at 16 and 19 meters above ground. This is very close to the ground. Variables change very quickly at the ground. This is really a hard thing for standard CFD models. We fare pretty well. An overview of all the complex sites. The terrain ruggedness index, if you remember, this Askava and Flowing Hill had around 3.3. The average of all the 6 validation sites we did was at 7.3. This is the summary of the wind speed profiles and the validation sites. And from those validation results, I'm deriving statistical values now, which describe how good our method fares. We had measurements from 30 centimeters to 78 meters above ground level, scattered over the globe in complex terrain. And it shows that the statistical analysis we have, if we compare measurement and experimental measurement and simulated data, is that we have a bias in average wind speed of 0.39 meters per second. Means on average we underestimate the simulated wind speed, and we have a standard deviation in the method of 0.73 meters per second. If I go into the power calculation side of things, this gives us a bias of minus 17 watt per square meters. Watt per square meters is the wind power density. This is the wind power that can theoretically be converted by a wind turbine. And we have a standard deviation of 36 watt per square meters. What does this practically mean for our method as it is right now, and we are thinking we can still improve? To give you an example of the uncertainty, I was looking at the 4 targets where it actually makes sense to install a wind power plant. We had Handarm, Lichteneck, Megler, and Nacelle Ridge with wind speeds high enough to use for energy conversion. If we look at the annualized experimental energy production that is possible at these sites, we see a year-to-year fluctuation because the wind is not constant over the years. The years fluctuate, the weather fluctuates. On average, we get a value, kind of floating average, but year-to-year fluctuation, we have 12% fluctuation on Handarm, 8% at Lichteneck. Reason for that is because we are lower at Lichteneck, and 17 and 12% respective at Nacelle Ridge. This gives an average annual energy production fluctuation of 12.7%, meaning 1 year I can produce 13% more energy at the same target than the next year. Our simulation method on average gives a variability of 14.3%, meaning our prediction error is already in the range of the yearly fluctuation. So, to summarize, the average simulation method we have now, the fluctuation of the method is similar to the year-to-year annualized energy production fluctuation at the sites suitable for wind power. How are wind power sites usually examined? Usually you put either a LiDAR box there, or a soda box, or a wind mast, and this usually comes with costs. And you usually measure at least a year. But if you put a wind measurement there, which is most exact, and measure for 1 year, that means you are not better than the method we have now. You don't have more information after measuring a year. So our method is already comparable to mast measurements, which are installed a year or less. But we do it at a fraction of the cost. Most sites, if they are really important, probably measure for 2 years and will probably try to increase that accuracy even more to be comparable to those fluctuations that happen within 2-year range. So we are already comparable to the state of the art, meaning mast measurements installed for a year or less. but our method will cost less. This is the message. What is the outlook from the project side? The immediate outlook is actually listening to you and answering your questions. And we hope you have many interesting questions for us to answer. And the next steps in the project and beyond will be, we want to increase the number and diversity of the validation sites, meaning we want to see how the method fares somewhere else. This means researching further, looking at tall tower data sets, or actually good instrument experimental data, and comparing our simulation with that. We want to optimize the runtime and the computational costs. And after that, we want to make the simulation accessible to engineers in the wind power industry. So develop a front end that is easily accessible. And further increase the post-processing and data analysis that is really needed by wind power experts. So as the project nears the end, some of those will be implemented in the projects and the others are outlook for developments after this project ends. And this is where our presentation ends, and I'm happy to answer your questions.